Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like number systems and their conversion used in digital electronics, De Morgan's theorem. Slide 1. Number systems used in digital electronics. Let's begin by understanding what a number system is. A number system is a way to represent and express numbers using symbols or digits. Each system has a base or radix, which determines how many unique digits it can use. The most basic number system in digital electronics is the binary system, which uses only two digits 0 and 1. This is because digital circuits have only two states, on and off. Next is the decimal system, which we use in daily life. It has a base of 10 and uses digits from 0 to 9. The octal system has a base of 8 and uses digits from 0 to 7. It is a shorter way to represent long binary numbers. The hexadecimal system uses base 16 and includes digits from 0 to 9 and letters A to F. It is very useful in computing and memory addressing. A bit is a single binary digit, either 0 or 1. A nibble is a group of 4 bits, and a byte is a group of 8 bits. These systems are crucial because they help digital devices store, process, and communicate data efficiently. Example: decimal 15 equals binary 1111, and hexadecimal F. Slide 2. Decimal to other number systems. Now we'll learn how to convert decimal numbers into other systems. To convert from decimal to binary, divide the number repeatedly by 2. Write down the remainders in reverse order. Example: decimal 25 right pointing arrow binary equals 11,001. For decimal to octal, we divide the number by 8 and reverse the remainders. Example: decimal 25 right pointing arrow octal equals 31. For decimal to hexadecimal, divide by 16 and reverse the remainders. Example: decimal 25 right pointing arrow hexadecimal equals 19. Each step of division changes the number into the new base. The final result is formed by grouping the remainders in the correct order. The concept of positional value is also important. It tells us that each digit's value depends on its position, based on powers of the base. These conversions are widely used in digital circuits for encoding numbers in a format that hardware can understand. Slide 3. Binary to other number systems. Now let's convert from binary to other systems. To convert binary to decimal, multiply each bit by 2 raised to its position, starting from the right with position 0, then add all results. For binary to octal, group the binary number into sets of 3 bits from the right and convert each group into an octal digit. To convert binary to hexadecimal, group the binary digits into sets of 4 from the right and convert each group into a hex digit. Using a lookup table for binary to hex makes the process faster, especially in programming. Binary is ideal for machines, but not for humans. That's why we use shorter formats like octal and hexadecimal for easier reading. Example: binary 101101. Right pointing arrow decimal equals 45. Right pointing arrow octal equals 55. Right pointing arrow hex equals 2D. The concept of grouping helps simplify large binary values and makes them more manageable for display and storage. Slide 4. Other systems to binary conversion. Next, we'll see how to convert other systems to binary. To convert octal to binary, just replace each octal digit with its 3-bit binary equivalent. Example: octal 57 right pointing arrow binary equals 101111. To convert hexadecimal to binary, replace each hex digit with its 4-bit binary equivalent. Example: hex 3a right pointing arrow binary equals 00111010. Since we already learned decimal to binary, you don't need to repeat that here. It's important to memorize binary equivalents for digits 0 to 7, for octal, and 0 to F, for hexadecimal, to speed up conversion. No need to convert to decimal first when changing between binary and octal, hex. This direct method saves time and is heavily used in computer architecture and microcontrollers. The term base expansion refers to expressing a number in another base using powers of that base. These conversions support systems like embedded controllers, digital meters, and display devices. Slide 5. De Morgan's theorem, rules and explanation. Now let's explore De Morgan's theorem, which is essential in logic circuit simplification. This theorem has two rules that help us convert expressions using NOT, AND, and OR operations. First law. NOT A plus B equals NOT A and NOT B. This means, if we take the OR of two variables and then NOT it, it is the same as noting both variables and ANDing them. Second law. NOT A, B equals NOT A OR NOT B. This means, if we take the AND of two variables and then NOT it, it's the same as noting both variables and ORing them. These laws are useful when designing circuits only using NAND or NOR gates, which are available in low-cost ICs. They also help simplify long and complex Boolean expressions. Let's verify with a simple example. A equals 0, B equals 1. A plus B equals 1 right pointing arrow NOT A plus B equals 0. NOT A equals 1. Not B equals 0 right pointing arrow 1, 0 equals 0. Both sides give 0 right pointing arrow so the law holds true. Complement means the opposite value of a binary digit. For example, complement of 1 is 0. Understanding De Morgan's theorem reduces hardware complexity and cost in real-world digital systems. Slide 6. Applications and significance of number systems in digital electronics. Lastly, let's understand how all these number systems are used in practical applications. They are essential in microprocessors and embedded systems, where binary logic is the foundation of operations. In memory systems, data is stored and accessed using binary addresses. BCD, binary coded decimal, is another format where each decimal digit is represented by a 4-bit binary number. These systems help detect and correct errors in data transmission using coding techniques like parity and checksums. They are also helpful in designing and minimizing logic gates using tools like Karnaugh maps. Using compact formats like hexadecimal reduces memory usage and improves processing speed. Number systems also support communication protocols like UART and SPI used in embedded and digital systems. They are used in digital displays such as those in calculators, digital clocks, and counters. Example: a digital clock uses binary counters internally to keep track of time and update the display every second.